Next problem is called palindrome partitioning. We are given a string S. We have to partition it such that every substring of the partition is a palindrome. So it reads both the same from left to right and right to left. We have to return all possible palindrome partitioning of S. Because it's all possible, we are generating, so that basically means recursion, and most likely because we are choosing the candidates, it means backtracking as well. Now, in the first example, we have A and B, so we can split it. So we have every substring has only one letter because every substring containing one letter is palindrome by itself. Or we can choose the first two A's because they read left to right and right to left the same, and then the remaining character will be B. If you have only one letter, that the only partition possible is to only have that letter, which is a palindrome by itself. So we just return that letter. The string can consist of 1 to 16 letters, and it only contains lowercase English letters. Now, when we take an example of, for example, we can start expanding basically the first string that we are taking as the candidate. So let's say we have A, B, C, D, and X, Y, Z, or these can be all like different like letters, whatever. It's not important. This is just for the explanation purposes. So the first thing that we will try in our first recursion call, we will check if we can form the valid palindrome partitioning by choosing our first string to be A. And then we will see if by the remaining strings can we split them in substrings so that each substring is a palindrome. Next thing that we will try, we will do A, B, C, and so on, and we will form the substring with two letters now. So it's A, B, and then we will see if the rest of the letters can form valid palindromes. And we will just continue doing that. We're continuing expanding our first candidate, first substring that can possibly be a palindrome, and then checking like with recursion if we can form palindrome valid palindrome by partitioning with all the other letters. So basically, that leads us to recursive relation, because if we can choose the initial split of the string, let's say ABC, if this string is a palindrome and the rest of the strings can form a valid palindrome partitioning, then the whole string can form and is forming a valid palindrome partitioning. This is the recursive relation then. The only thing else to note is that if we choose AB to be our first string for all the rest helper function calls, we will not be able to choose these elements again. So instead of like looping from 0 to the end of the candidates, we will be looping from start, so that we can only reuse one element once. So we cannot reuse it in any successive helper function calls. If you use it in the first call, all the rest letters are free for us, but not these two letters. So that's why we are using the start, and we are incrementing it every time. So it reflects that we cannot use the letter that we have used in the previous helper function call. So basically, this will translate to a classic backtracking problem where we have a main function and we are calling the helper function recursively, each time passing the start as the next start of the next successive helper function call. Now for the time and space complexity. For space complexity, because we will have total multiple strings, but they all add up to a string of length n, which is the initial string. So that will be our space complexity, and also the recursion tree maximum depth, because every single letter in the string can be partitioned. So we can partition it so every single letter is a substring on its own and a palindrome on its own. So the maximum depth of the recursion tree would be the number of letters that we have in the initial string. So both of them lead us to a linear space complexity. Now for the time complexity, it's easy to understand it once we show it an example. Let's just assume we have this string, and these little dots between the strings mean that if we choose the dot, That basically means that we are merging A, B, and trying to form the valid palindrome with the rest of the letters. If we don't choose the dot, the dot remains. Basically, we are not skipping it, and the A and B are two different substrings. So basically, we have two options: either to choose the dot or not to choose it, and they are in total n-1 dots. So our time complexity will be 2 to the n-1. Or if you can put less restrictive to time complexity 2 to the end. And because we will be copying also the string that we have built so far, we will have the classic multiplier, the standard multiplier end. So this will be our time complexity. As always, we start by declaring a result, which in our case will be a list of substrings that form valid palindrome partitioning. Each substring in that partitioning is a palindrome. Next, we will call our helper function, and at the end, we just return the result. And the result will contain basically all the valid partitioning. Next to the our helper function, we are passing just the string as the set of candidates. We are passing the start, which declares from which candidate we can start to choose from, basically. And the current list will be the list of like basically representing our current partition. It will be a list of substrings that we have managed to partition so far. The result will be the result that's passed from the main function, and if there is a valid partitioning, the current list will be added to the result, which brings us to our base case. If we have length, if the start is basically equal to the length of the string, that means that we have traversed over all the letters inside the string S. That means that we have a valid partitioning, and we can add our current list to the result and go up in the recursion tree. So we just return from the helper function. Next, as we said, we are not starting from the zero. We are starting from the start in each successive helper function. That means that we will not be able to reuse the letters that we have used inside the previous up the recursion tree, if you will, helper function calls. Next, we will check if the current substring that we choose basically from the start, and we are slowly expanding the end of our substring, and we check if the that substring is a invalid palindrome. We are using the isPalindrome function that we will declare later. If it is, we add that substring to the current list, and we call the helper function recursively by incrementing the next starting position. Once we are done with the helper, so when we get back to this call of the helper function, we will have to backtrack. So we remove the last element that we have added to the current list. For our isPalindrome function, we just take a parameter s, and we will have two pointers, one starting from the start of the string and one at the end, and we will basically move them in the opposite direction, and we will be checking if the letters that both of the pointers are pointing to match. If they match, we will just continue on incrementing our start pointer, moving it to the right, and decrementing our end pointer, moving it to the left. And if we traverse and basically all the letters and the start and end match, and they are at the same position, we just return, because that means that the string is a valid palindrome. If at any point we find mismatch between the letters that start and the end pointer are pointing to, we just return false, because we know that that string is not a palindrome.